Potential energy cannot exist in a zero volume. Potential energy is a fundamental concept in physics, representing stored energy that can be released to do work. It is present in various forms, including gravitational, elastic, electric, and chemical potential energy. Each of these types depends on the spatial relationships within a physical system. For instance, gravitational potential energy relies on the relative position of masses, while electric potential energy depends on the spatial separation of charges. A key aspect of potential energy is that it inherently requires a spatial framework, namely, volume, to exist. Here, I will explore why potential energy cannot exist in a zero volume and how this requirement reflects deep principles of physics and metaphysical considerations about space, existence, and causality. 1. The spatial basis of potential energy. Potential energy is fundamentally relational. It exists due to the interactions between entities within a spatial context. For gravitational potential energy, this context is the distance between two masses. For electric potential energy, it is the distance between charges. In all cases, potential energy is not an inherent property of a single point but rather an attribute of a system of points separated by some finite volume. A zero-volume scenario implies the absence of spatial separation, which would eliminate any possible interaction or relationship between the entities involved, thus nullifying potential energy. For example, in a gravitational field, the potential energy between two masses m1 and m2 separated by a distance r is given by U equals minus gm1 meter 2, r as r approaches 0. A hypothetical zero-volume condition where the masses occupy the same point in space. The formula becomes undefined or approaches negative infinity. In practical terms, this means that without a spatial separation, there is no meaningful way to calculate or even conceptualize potential energy. 2. Why zero volume eliminates interaction. Interactions that give rise to potential energy require spatial separation, which inherently involves non-zero volume. This volume allows entities to have a measurable position relative to one another. When spatial separation approaches zero, entities essentially merge, and the very basis for potential energy, relative position, disappears. Consider electric potential energy, where the force between two charges q1 and q2 separated by a distance r is given by U equals kq1 q2, r if r equals 0. Then U becomes undefined because the concept of potential implies a measurable field between entities. Fields cannot exist in a point with zero volume because they need spatial extension to manifest force over distance. Thus, without volume, there is no capacity for the field, and hence no potential energy can arise. 3. The role of volume in field theory. In physics, fields such as gravitational, electric, and magnetic fields operate within spatial volumes, filling regions of space and exerting influence across distances. Fields are the carriers of potential energy, creating a structure within which energy can be stored and eventually released. A zero-volume field is contradictory because it implies an influence with no extent. Fields operate as continuous regions, with each point within the field contributing to the potential energy through a finite spatial arrangement. For example, the gravitational field produced by a mass creates a potential energy gradient in the surrounding space, enabling objects within this field to have potential energy relative to the mass. Without a spatial dimension, i.e., in a zero-volume context, there would be no field, and hence no potential energy could exist. Fields require volume, as their properties are defined over a continuum of points in space. 4. Quantum mechanics and the need for space. In quantum mechanics, even particles considered point-like have probabilistic spatial distributions. Quantum particles are described by wave functions, which represent the probability of finding a particle in a given region of space. Potential energy in quantum systems, such as the electric potential energy between an electron and nucleus in an atom, relies on spatial probability distributions. Without volume, the wave function collapses to a singularity, making potential energy undefined within such a framework. Additionally, Heisenberg's uncertainty principle states that it is impossible to precisely define both the position and momentum of a particle. A zero-volume scenario would imply absolute certainty of position, thus violating this principle. Therefore, quantum mechanics also implies that zero volume is inconsistent with the spatial requirements for potential energy, as it would contradict the fundamental properties of particles and fields at the quantum level. 5. Philosophical implications. Space, existence, and potentiality. The dependence of potential energy on volume touches on deep philosophical questions about space and existence. In classical philosophy, potentiality, the capacity for something to change or produce an effect, requires a real, extended context within which potential can manifest. Potential energy represents this concept in physical terms, as it is the capacity to perform work based on spatial relationships. Aristotle's philosophy, for example, holds that potentiality must exist within an actual framework. A zero-volume context, devoid of spatial extent, would be entirely actual, in the sense of being entirely realized without extension or potential for change, thus lacking any potentiality. Philosophically, potential energy relies on the possibility of change within a spatial structure. Without volume, there is no possibility, and hence no potential energy. 6. Potential energy and the necessity of spacetime. In the context of modern physics, spacetime, the four-dimensional continuum of space and time, provides the framework within which energy and matter interact. The concept of potential energy assumes that entities exist within spacetime, allowing them to interact at finite distances. Zero volume would imply the absence of spacetime, thereby eliminating any framework for potential energy. Since potential energy is tied to the configuration of objects in space relative to each other, spacetime itself becomes a prerequisite for potential energy. Even the notion of zero-point energy, in quantum physics, which represents the lowest possible energy state in a vacuum, still presupposes a spatial and temporal framework. Zero-point energy does not equate to zero volume, instead, it describes the residual energy within a field. Thus, even this foundational form of energy requires spacetime as its setting. Conclusion. The spatial requirement for potential energy. Potential energy is inseparable from spatial configuration, as it depends on distances and interactions that occur within a physical volume. Zero volume would eliminate all spatial relationships and interactions, rendering potential energy non-existent. From gravitational and electric fields to quantum mechanics and philosophical concepts of potentiality, potential energy fundamentally requires a spatial framework to exist. The spatial nature of potential energy not only reflects the laws of physics but also underscores the relationship between space, matter, and energy that shapes our understanding of reality. Without volume, there is no framework for the relational dynamics that give rise to potential energy, affirming that potential energy is necessarily bound to spatial dimensions and cannot exist in a zero-volume scenario. Thanks for watching. Please like, share and subscribe, and comment below if you agree or would like to add your thoughts. If you would like me to respond to your comment, please make a level 1 comment directly below the video. I will respond to all polite level 1 comments even if it takes me a while, due to other commitments.